Welcome to how to determine the enthalpies of reactions. And in this video, I really show that there's three different scenarios that we encounter. The first one is where we're using a calorimeter. And a calorimeter is going to help us determine how much heat is being transferred. Now remember, energy can be transferred as either heat or by work. But in the coffee cup calorimeter, or in calorimeter, where we're talking about constant pressure, we're really just looking at the heat being transferred, which is equal to the change in enthalpy of that reaction. So under that scenario, we know we have the system and the surroundings. Whatever is released by the system has to be gained by the surroundings, or vice versa. And so we know Q of the system plus Q of the surroundings has to be equal to 0 because energy can neither be created nor destroyed. Well, we could replace Q of the system by just talking about Q of the reaction. And we could replace Q of the surroundings as Q of the solution in a coffee cup calorimeter. So, really, if we just rearrange this equation, we get minus Q of the reaction is equal to Q of the solution. And Q of the solution itself is equal to the mass of the water times the specific heat times the change in temperature. Now for a bomb calorimeter, just slightly different. Now we can still think of we have Q of the system and we have Q of the surroundings. But we have to remember that Q of the systems could be rewritten as Q of the reaction. But our surroundings now include both the solution that's inside the calorimeter as well as the calorimeter itself. So we can rearrange this to minus Q of the reaction is equal to Q of the solution plus Q of the calorimeter. Now Q of the solution is still going to be that same MC delta T, whereas Q of the calorimeter, the mass is usually already incorporated into the C of the calorimeter, so we just take that times the change in temperature. And we can ultimately solve for minus Q of the reaction, which then is Q of the reaction is equal to the change in enthalpy of that reaction. Now we could also look for the enthalpy of a reaction if we were given, or if we know Hess's law, and if we're given the delta H for other reactions. So in this case, we could say that we have a reaction of A going to B with a delta H of 25 kilojoules, C going to B with a delta H of minus 10 kilojoules, and C going to D with a delta H of 15 kilojoules. And what we're looking for is the delta H of the overall reaction of A going to D. Well, if we just think about looking at what's on the reactant side and what's on the product side, we see that we can't cancel many things out. But if we were to swap the second reaction, C going to B, and reverse it, we could then cancel out B and we could cancel out C. So if we just reverse this reaction and rewrite it as B goes to C, we know then that we can change the delta H value here, where it's no longer a negative 10 kilojoules, but in fact we make it a positive 10 kilojoules, which now means that A going to B, B's can cancel, B going to C, our C's can cancel, and now we're going to be left with A going to D, and we can add the delta H's of these reactions together, where we take 25 plus 10 plus 15 is going to give us a total of 50 kilojoules for this reaction. Now a third way that we can look for the enthalpy of reaction is through Hess's law if we're given the enthalpy of formations of the products and the reactants. And in that problem then, we know the equation for Hess's law here is that the delta H of the overall reaction is equal to the sum times the number of moles of the enthalpy, change in enthalpy of formation for each product. We take the total of that minus the sum of all the moles of the enthalpy of formations of each of the reactants. We add all that together, and then we can solve. That's really the three different scenarios on finding the enthalpies of reactions.